Okay, in this video, it's going to be the last in a series of videos on Taylor series of complex numbers. We're going to look at the Taylor series of these functions expanded about the given points. In particular, example A, we have looked and we've worked it out in our part 2 video. And this is the expression that we got for the Taylor series, but we were using the method of repeated differentiations. And if you have watched all our videos, I think you will be aware that we are encouraging these clever methods of using standard results rather than repeated differentiations, because those ones, they work much quicker. So this time we are going to work this out without repeated derivatives, by just using standard results. So this one is an exponential, so the result for the exponential function at 0 is e to the x equal to the summation x to the power n over n factorial, and the radius of convergence for this is infinite. So the thing that we are going to do then for this function here, since the point about which we are expanding is not the origin, is introduce a transformation so that z equals to pi is the origin. So if we let u be equal to z minus pi, then z is going to be u plus pi. So from this, it means that f of z equals to iz over 2, we can write as e to the I over 2 u plus pi. So this is going to be e to the I u over 2 times e to the I pi over 2. E to the I pi on 2 is just I. And so now this is just going to be the Taylor expansion of E about the origin, because when u equals to 0, then z is equals to pi. So this is going to be I into the summation of I u over 2 to the power n all over n factorial. And of course then I u over 2, this expression or this expansion is going to be convergent so long as that is magnitude of that is less than infinity. So this is going to be I to the power n u to the power n all over 2 to the power n factorial. Then what we can do is we can multiply by the u into the summation by the I. It's going to be I to the power n plus 1. Then u is z minus pi. So z minus pi here to the power n 2 to the power n times n factorial. This thing, of course, is going to give us magnitude of u is less than infinity, which in terms of z is z minus pi less than infinity, which is exactly the same result as we got before. Okay, so that's just using your standard Chlorine series and the geometric series result. That's all you need really. So Chlorine series for exponential, sine, and cosine. That typically should be good enough for most of what you need to do. Right now, we're going to give you a few minutes just have a go at this one without repeated differentiations. So the other advantage of this approach is straight away you get the closed form expression of the summation the closed form expression of the Taylor series in summation notation form, instead of getting your first 4 terms and you can't exactly see where the pattern is going. All right, so if you want to have a go at this, just pause the video, and then after that you can, when you continue it, then you can compare with our solution. All right, at this point we're going to scroll down to our solution for part B. We would like to thank you for visiting our channel and watching this video. We do hope that these videos are useful to you. We do implore you to subscribe to our channel to support us so that we can produce more material of this nature. If you've got any questions, comments, you can post them in the comment section below. Okay, so for part B, we've got sine 3z. Want the Taylor series of this about z equals to pi on 2. So I'm going to let u be z minus pi on 2. Then f of z is going to be sine of 3 into z minus pi on 2. And then this is going to be sine A cosine B minus sine B cosine A. And then cosine 3 pi on 2 we know is 0. So that means this term here is 0. And sine 3 pi on 2 is going to be -1. So that means what we have here is simply cosine 3z. Okay, there's an issue here. Just one moment. Right, sorry about that. What we should do is after making u equal to z minus pi, then we say z is equals to u plus pi on 2. And therefore, we're going to have here sine 3 into u plus pi on 2. And so this is going to be sine 3u cosine 3 pi on 2 plus sine 3 pi on 2 cosine 3u. Okay, and then as before, cosine 3 pi on 2 is 0, and sine 3 pi on 2 is equals to -1. So this thing is simply equal to the negative of cosine 3u. Now, the Chlorine expansion of cosine is cosine of x equals to the summation of -1 to the power n, x to the power 2n, all over 2n factorial. And this has got an infinite radius of convergence. So that means for our f, we're going to have the negative of summation of -1 to the power n 3u, which is our argument here, to the power 2n divided by 2n factorial. So of course we're going to get that condition on the radius of convergence. And so this is going to be the negative of 3 to the power 2n, u to the power 2n, -1 to the power n, 2n factorial. 3 to the power 2n is the same as 9 to the power n. U to the power 2n. Now, so this we can write as -9 to the power n. U instead of z is equal to z minus pi on 2. So that's going to be z minus pi on 2 to the power 2n, all divided by 2n factorial. And then of course the radius of convergence is going to be infinite here. And that brings us to the end of that one. Thank you.